So this third handout then on torsion and shafts relates only to circular shafts, maybe hollowed or solid, maybe hollow shafts, often solid but certainly circular. So something that looks like this, where we've got some sort of resisting torque, so it's being held maybe at this end here, and then it's being twisted in this sense, and so we've got some sort of twist going on. And we've got a formula that we're going to use to describe this thing, which are almost exactly the same idea as the bending equation that we've already looked at. So what we were doing last week on the bending equation applies pretty well to this, just different formulae. In determining the torsion equation, certain assumptions are made. So just like the bending equation, then there are certain assumptions made. Radial lines remain straight after twisting. So by that I mean lines drawn out from the center. These radial lines here drawn out from the center of the shaft will still be straight after twisting. So there's no deforming going on inside the material. The whole thing's just been twisted. Circular cross sections remain plane, no distortion. Twist per unit length is constant, so it's uniformly distributed across the shaft. As you might expect, these sorts of assumptions are being made. So everything's happening over quite small distances. Nothing major is happening. No deforming is going on inside the shaft. So long as that's the case, then we can apply this bending equation, torsion equation. We define these terms here. T for the torque, the applied torque to the shaft. And then we calculate something called the polar second moment of area. So that has the same sort of meaning as the second moment of area that we were looking at in the bending moment equations. And it's to do with the way that this torque is distributed across the area of the shaft. Tau, this Greek letter here, tau, is the shear stress induced. So if that's a new letter to you, tau, part of the Greek alphabet, we use to represent shear stress. R being the radius of the shaft. G is something called the shear modulus, which is to do with the rigidity of the thing, how much it resists shear forces to it. Theta.
So can it mean different things if we're using that?
Yes, it can. Oh yeah, yeah. It's very common to use the same symbol to mean different things, but within the context of this situation, then that's what it means, yeah. There is only a finite number of symbols, so we have to use them over and over again, unfortunately. Theta, angle of twist, so if we manage to twist it, the angle of twist is theta, and now the length. So with those values, we end up with the torsion equation, which is here, which is worth making a note of. That's what we're going to be using, and I think the derivation for the torsion equation follows on in the notes. That's something that we may look at when we come to look at integration in the mathematics, but really that's just there for interest. What you actually need to do is to be able to apply this torsion equation. And you can see it's very similar to the bending equation. It's just a series of ratios. We're saying the ratio of the torque to the polar second moment of area equals the ratio of the shear stress to the radius of the shaft equals the shear modulus times the angle over the length. So just like the bending equation, we only ever use two of the ratios. So tutorial questions are going to involve deciding which ratios to use and then rearranging it maybe to find, say, torque, and then putting the numbers in. So similar ideas as we'll see. Note this equation only applies to shafts of circular cross-sectional area. So when we write down, which we will do in a second, the polar second moments of area, we're only going to do that for circular shafts. So formally, for the second moment of area, for a solid shaft, is very similar to the one for the bending, the second moment of area for the bending equation. If we use capital D for this one, actually, And for a hollow shaft, like we did for the bending equation, yeah, yeah, is it cubed
Sorry,
to the power 4? Yeah, I'm trying to remember it. I'm going to check it in a second. I think it's to the 4. Let me just check it. Over 36. In other words, we're just taking away the hole in the middle. So this is a solid shaft, 36. Is it? Just pause. A correction on that, the polar second moment is pi d to 4 over 32. And where that comes from, again, we might look at when we come to the maths. We'll look at, it's an integration process to arrive at the value for the second moment of area or the polar second moment of area. But really, we just need to be able to use them. So there are the formulae, where the first one is a solid shaft with a diameter of d, and this is a hollow shaft with an outer diameter of d and an inner diameter of little d. So those are the formulas we use to find the second moment of area. So there's two examples in here that we're going to go through where we apply these equations, torsion equations, and then there's some tutorial questions at the end that follow on that I'll let you have a look at. Okay. The method is almost exactly the same idea as we use for the bending equation. Probably a good idea to draw it out, put the values on, make sure you're in the base units, and then start thinking about what parts of this equation we're going to use. If we do that, then we can see that the length 1.5 meters, the diameter is 50 millimeters, which I would write in meters, so everything's in the correct unit. I'm given the value for the stress, tau, which is 70 meganewtons, so that's 70 times 10 to the 6. I'm given the value for G, this modulus, 80 giganewtons per square meter, so 80 times 10 to the 9. And I've got to find theta because it's twisting. What's the maximum amount of twist in the shaft? So we're told that the maximum stress it can take is 70 meganewtons per square meter before we start to deform it. So what's the maximum amount of twist we can get in this thing? Find theta. Give you this information. So as with the bending equation, first step is to write down this equation that is useful in this situation. So there is the torsion equation, T over J equals tau over R equals G theta over L. So which ratios are we going to use? Remember, we're after theta. We can find, we can find the second moment of area, the polar second moment of area. So we can find J. So we've got this. Do we know T, the tension? What's the torsion in this thing? No, we don't, do we? Do we know tau? Yep. Do we know R? And we want to find theta, so in fact it's these two ratios we're going to use. So actually, although we could find J, there's no point, we wouldn't use this ratio. So we're not going to use this part of the torsion equation, we're going to use the other two ratios. And we want to find theta, so we need to rearrange this for theta. So multiply both sides by L to get rid of L on the right-hand side. Divide both sides by G to get rid of this bulk modulus. So we get tau over R times L over G equals theta. So therefore, theta equals tau L over RG. And now all we have to do is put the numbers in and we get the value for theta. So theta turns out to be 0.0525 if we calculate it. So what is that? What is it? It's the angle. So what must it be measured in this case, do you think? Yeah, it'd be measured in radians, yeah, okay, in radians. And so the radian is actually a proportion of a turn. That's from the definition of the radian. So it will automatically come out in radians using this equation. If you want it in degrees, we've got to use to convert it.
One full turn is 100 radians.
No, 1 full turn is 2 pi radians. So to convert, 2 pi radians is 360 degrees. 2 pi radians is 360 degrees is the conversion factor that we use. So therefore, pi is equivalent to 180 degrees. So if I want to convert from radians to degrees, what I really need to know is what 1 radian is. And if pi radians is 180 degrees, right, or pi, yes, so therefore 1 radian equals 180 divided by pi. So 0.0525 radians will be 0.0525 times 180 over pi. So therefore theta in degrees, which you may well want it in, equals 0.0525 times 180 over pi. Comes to 3 degrees. Okay. So one word of warning on this: if theta is involved in this torsion equation, it must be in radians. So if you're given a value for theta in a problem, or you've calculated your angle of twist, and you've measured that in degrees, if you're going to then put that into the torsion equation, you need to convert that to radians. So it's worth just finishing off by noting this conversion factor. So therefore the conversion factor for radians to degrees and back again, it's worth remembering. We've already got the one from radians to degrees, so radians to degrees times by 180 over pi. Similarly, from degrees to radians, we go the other way. Times by pi over 180. But the conversion factor that's worth remembering is this, that 2 pi equals 360 degrees. Once you've got that in your head, and we all know that 1 complete turn is 360 degrees, then you've just got to remember that that's equivalent to 2 pi radians. So then you can work out what these conversion factors are. Okay? So it might also be worth going back to this torsion equation that we wrote down at the start here and make a note. Theta of the angle, actually it's here already, measured in radians. So if you're going to put it in and it's in degrees, must convert to radians before you put it into the equation. So looking at example 2 in here, so again I'd recommend you draw it out and then put on the values, making sure they're in the correct units. Lengths and diameters in meters, and base units for other things. So for this question, we need to find out what the torque is. What is the force that's being exerted on this shaft to twist it? And the relationship between power, torque, and angular velocity is given by this equation here. Power equals torque times angular velocity. So in this question, we need to use this formula. If the power transmitted by a shaft is quoted, which it is in this case, then the torque can be found using this equation. Power is torque times angular velocity. So we rearrange that formula to find the torque. Torque is power divided by the angular velocity. So now we've just got to find out what the angular velocity is, measured in radians per second. So we've got to work out what the angular velocity is. To help us find the angular velocity, we're given the frequency. And the frequency effectively is this, 1,650 RPM. And we want that frequency in hertz. So we need to convert the frequency to cycles per second, revolutions per second, and then use a formula that relates the angular velocity and the frequency, which is that omega equals 2 pi times the frequency. So we could put this formula, omega equals 2 pi f, together with the power formula, power equals torque times angular velocity, to be able to find the angular velocity given the frequency. So we've got a few formulae we've got to use now. We've got the torsion equation, this power equation that relates power and torque, and also knowledge of what we mean by angular velocity in terms of the frequency of something that's rotating. So a plan for questions like this, because it can get quite complicated because we've got three formulae here that come in. So having these three formulae together will be useful to help you see your way through it. So I would suggest that number one, you start with the torsion equation, because that's the one we're going to end up using in the end, this torsion equation here. And look for a ratio that we know. Do I know G and theta and L, or do I know T over tau over R, or do I know the other ratio? Am I given that information? Or can we find one of those ratios given some other information, like I'm told the power or I'm told the frequency, something like that. So as soon as you see power coming into it or frequency, you know that I'm going to be concerned with the angular velocity here, which means I can use this equation to find the torque. So I know this value in here. And in that case, I probably need to find out what J is. So I need those other formulae for the polar second moment of area. So we may need, if we need J, this polar second moment of area, then we also need those equations. So we might actually need recourse to another two equations for the polar second moment of area. Then once we've identified the ratio that we can find, and we've found all the relevant values, look for the ratio that includes what we want to find. And then rearrange. And this plan, by the way, this general plan, could easily apply to the bending equation because it's exactly the same idea. So in this example, let's write down the torsion equation and then list what we know. I'm trying to sort of suggest ways to get through a problem if you're stuck. Drawing it is always a good idea. Once you've drawn it, maybe listing what you know is a good idea. So there you can see what equations apply, which ones we're going to have to use in this case, bearing in mind that the main one we're going to be concerned with is this torsion equation here. And what are we after in the question is something else we need to consider. So what we actually asked to find here, what is the factor of safety being used? Yeah. So what are we actually after? The safety factor, we're after tau, yeah, the stress. So we're actually trying to find, so this is the maximum stress. So what we're actually having to do in this question is to find the stress, and then compare this with the maximum stress. No, that's right. We've got to find it and then compare this with the maximum tau as a percentage, I guess, to find this safety factor. And I'll Yeah, that's right. Or per second, yeah. What for? Didn't you? Yeah. Yeah. Hertz means revolutions per second. You divide 1,650 by 60. No, that's telling me it's 1,650 revolutions every minute. I want to know how many revolutions it does in a second. So divide it by 60. Yeah. Okay. Which gives 27.5. Okay. And now you times that by 2 pi, which gives this. Hundred and 50 times 10 to the 3. Yeah, so I didn't make that clear. Divide by 60 because we know RPM, revolutions per minute, we want revolutions per second. Okay. And tau equals TR over J, so J. 1.83, did you say?
1.83 times 10 to the 6.
Yeah. And that will be in newtons per square metre, is it? Unit. Oh, no, that'll be in meters to the 4, won't it? Of course it will. Meters to the 4, what am I saying? So therefore, tau equals T, what did we say it was? T R over J, I can't remember now.
TR over J.
TR over J. Yeah. So that's 886 times R, which is 0.0375, over J, which is 1.83, times 10 to the minus 6. No? Yeah, sorry, am I going a bit quick? I was only doing it, you were doing it at the same time as me. I was just going through it while you were doing it, okay? But yeah, if you want to make a note of it. Is that far enough on there? Yeah. And newtons, tau, it's a force, so it'll be newtons. Torque. Oh yes, it works. No, it's not a force. It's not a torque, is it? It's a stress. So yeah, newtons per square metre. Yeah. So that's what I get the stress to be, about 17.8 times 10 to the 6 newtons per square metre. So now the factor, the safety factor, it looks actually it's not a percentage, so it's just as a number. It's just you just divide the maximum by what you're putting in. So the safety factor equals maximum value divided by calculated value. So let me just record this little bit here. So right, do they? Yeah. Okay.
You've got a factor of safety close to 10 and you account.
Yeah. So well, this is perhaps a bit under then. Right, Chris, did you take on that point James was making? So we're normally looking for around about 10. Perhaps I'll add that here. So the safety factor should be around about 10. Okay.